For the past few years in AI development, the golden rule has basically been bigger is always better, right? The whole industry just assumed that if you scale up a model's parameter count, feed it more data, and throw more compute at it, you're automatically going to get a smarter, more capable, and crucially, a more reliable system. But we're jumping into some major AI news today for this explainer because a recent dive into benchmark data is completely flipping that assumption upside down. It turns out these massive models often care way more about sounding confident than actually being right.
So, does a bigger AI actually mean a smarter AI? We really need to challenge how we're evaluating these systems because this new data is completely upending the industry's scaling laws. Major AI labs are actually starting to second-guess this endless race for more parameters. The data is showing us that, sure, making a model bigger might make it amazing at matching patterns or writing a really eloquent essay, but it doesn't necessarily make it more truthful. Actually, sometimes it literally does the exact opposite.
86%. Just let that sink in for a second. That is the hallucination rate of GPT-5.5, literally one of the largest, most widely used models on the planet when it's put through a critical uncertainty benchmark. What that means is when the model was asked a question it genuinely did not know the answer to, 86% of the time, it didn't just admit it was stumped, it confidently made something up.
All right, moving into Section 1, the hallucination benchmark. Let's look at how we're testing AI's factual limits and why this is turning into a massive headache for these trillion-parameter models. To really get to the bottom of this, researchers are using something called the AA Omniscience benchmark. And what's cool is this isn't just a test of hard trivia questions. It specifically targets something called conditional fabrication. Basically, it tests the probability of a model hallucinating when it's uncertain. Simply put, if the AI flat out doesn't have the ground truth, will it confidently lie to your face, or will it just say, hey, I don't know? And the results here brilliantly expose the paradox we're dealing with right now. You've got massive, proprietary giants like DeepSeek V4 Pro hitting an absolutely staggering 94% hallucination rate, and GPT-5.5 right behind it at 86%. But then, you have a much smaller model, GLM-5.2, scoring just 28%. Other heavyweights like Fable 5 and Opus 4.8 fell somewhere in the middle. The biggest names in the industry are basically failing the hardest when it comes to just admitting they don't know something. So, we really need to talk about what GLM 5.2 actually is. It's an MIT-licensed open weights model developed by ZAI. It has 753 billion total parameters, but only about 40 billion are active during inference. To put that in perspective, that's roughly half the size of the 1 to 2 trillion parameter behemoths it's going up against. And yet, despite being a total lightweight in comparison, it absolutely crushes the competition when it comes to factual reliability.
So, why is this happening? Let's get into Section 2, Conditional Fabrication Explained, and break down the actual training mechanics behind these hallucinations.
This all comes back to that concept of conditional fabrication. See, because massive models are trained on these astronomically large mountains of highly factual data, they become, well, incredibly eager to please. The way they're trained, the actual reward signals they get during reinforcement learning, literally rewards them for guessing rather than admitting ignorance. They learn pretty quickly that spitting out a highly structured, plausible-sounding answer is somehow better than just hitting the brakes and saying, I lack the context to answer this. To really put this to the test, researchers set a brilliant trap. They fed a super complex Python asynchronous prompt to both DeepSeek V4 Pro and GLM 5.2. But here is the catch. They deliberately baked a fundamental architectural flaw into the prompt. They basically asked the models to design something that is technically impossible to execute in Python without causing a total system deadlock. The results were honestly mind-blowing. DeepSeek V4 Pro, this massive 1.6 trillion parameter brain, spent nearly 4 minutes, 3 minutes and 52 seconds to be exact, wasting compute power just to confidently generate a structurally perfect, completely useless block of false code. It wrote thousands of tokens for a solution that would never ever work. But the smaller GLM 5.2, it took just 12 seconds to spot the logical deadlock and basically told the user, nope, these constraints are technically impossible. If you're not super into the coding side of things, the source article had a fantastic analogy for this. What the giant DeepSeek model confidently tried to program was as physically impossible as asking a delivery driver to drop off packages at 3 different houses at the exact same time without ever stopping the truck. The smaller model immediately saw the paradox, while the massive model just pretended it could drive a magic truck. And that perfectly transitions us into Section 3, the AI trilemma. and how we are completely redefining model evaluation. We are looking at a huge paradigm shift here because real-world truthfulness is finally separating from just dominating a leaderboard. We're entering an era where training and selecting an AI means balancing this unsolved trilemma. First, you have raw capability. Can the model actually do the complex reasoning? Second is uncertainty calibration. Does it know when it's out of its depth? And third is computational efficiency. How much compute are we burning through? Because as we push closer and closer to artificial general intelligence, just throwing more parameters at the wall is actively ruining that second step. It's making uncertainty calibration worse. But hey, let's be totally fair here. We can't just look at conditional hallucination in a vacuum. We have to look at the full mathematical picture. When you adjust a model's conditional fabrication rate against its overall raw accuracy on really hard tasks, the gap does narrow. For example, Opus 4.8 has a much higher raw accuracy at 47%, so when you do the math on its conditional rate, its absolute everyday hallucination rate is about 19%. GLM-5.2 has a lower raw accuracy of 25%, which gives it an absolute hallucination rate of 21%. So while the giant models do fake answers way more often when they're confused, they are technically confused less often overall on complex tasks. So, knowing all that nuance, let's jump into Section 4, Building Reliable Systems. What are the actual developer takeaways and mitigations we need for our deployment pipelines? I think the absolute most critical takeaway from this explainer is a fundamental mindset shift for developers and engineers, and it's summed up perfectly in this quote. You simply can no longer trust an AI just because it's some massive multi-trillion parameter giant. We have got to start treating all LLM outputs as probabilistic drafts. They are highly educated guesses, guys, not definitive ground truth. Instead of blind trust, you've got to put up some guardrails. I'm talking about concrete control mechanisms. You need verification layers, like unit tests or even secondary smaller models, just to fact-check the giants. You need to set strict confidence thresholds. You should absolutely be enforcing structured outputs, using strict JSON schemas to catch those errors early. And maybe most importantly, you need fallback routing and task-specific evaluation, meaning you test these models against your actual daily workloads, not just some theoretical benchmark. A really pragmatic approach that the data points to is to just mix and match. Because GLM 5.2 has that open MIT license, you can build it directly into your pipeline as a low hallucination fallback. Use it for the tasks where factual reliability is absolutely non-negotiable. Then you can reserve the massive, expensive proprietary models for deep, complex reasoning tasks, where their higher base accuracy actually justifies the compute cost and the risk of them making things up. So I'll leave you with this final thought as we wrap up today's explainer. We are living in an era where the absolute smartest models on the planet are also the most confident liars when you back them into a corner. So how are you going to redesign your own systems? As these massive models become totally commoditized, are you going to prioritize theoretical capability, or will you build architectures that actually guarantee the truth? It's a trilemma every single developer is going to have to face. Thanks so much for joining me to unpack all this, and remember to always keep questioning the data.